Hi, David Vizard here, and you are watching PowerTec 10. Give me a few minutes of your time, and I'll give you the benefit of not only 50 years of race-winning engine building experience, but also 30 years of successfully teaching it at university level. So what's the subject of this episode of PowerTec 10? Well, if you're a Ford fan, you're going to like this. It's a rundown on a very successful and very functional small block Ford cylinder head. Ever wonder why this series is called PowerTec 10? I sometimes ask myself that, but there was an original sound reason. My original idea was to have a 10-minute short video to highlight certain important but rarely talked about items in performance. Well, it turns out two things. One, I have way more of these things to talk about, and two, they take up more than 10 minutes, right? So I really should name it PowerTec 30 because that's nearer it, but anyway, that's beside the point. What's our subject for today? It's a Ford head, a small port Ford head from AFR. Now I do have some experience with this from way back. Unfortunately, I can't remember much of it, and so I thought I'd start from scratch here and look at their current one, but I had great expectations because it was one of the top performing heads, along with one from Edelbrock and one from Dart. So what have they done that may be different now? Well, let's get into that, because this head turns out to be something a little more special than you might think. First, let's take a look at the basic cylinder head stripped of its hardware. We can see from this that it's a fully CNC ported head. Now, you may look inside the ports and think, well, that's a bit of a coarse finish there. Can they truly justify that? I don't know if you can see it here, but you probably can hear the screwdriver going over it. Well, I have cleaned up some of these heads to just make the finish an emery roll finish, and two things are evident. One, it has almost no effect on the flow, and I'm talking about just a surface finish change here, not a shape change. And two, it has no effect on the horsepower either. And I think, or I'm sure, if you actually polish those ports, you'd probably lose a bit of power. My guess is that these ridges here, in some way, shape or form, act like not so good golf ball dimples. In other words, they're better than a flat port, but not quite as good as golf ball. Right, and their golf ball finish is very expensive to do. Anyway, there we go. So 165cc intake port, 70cc exhaust, 1.9 inch intake valve, 1.6 exhaust. The valves are very good here. Let me show you. They are a lightweight design, flat back, because that's what the port likes. But the best virtue is their 5/16 stem, or 8mm. Right, and as such, they are very light. We'll get into that in a moment. I'll show you the weight difference between that. And here's the exhaust, tulip shaped on the back, and this is usually a form that works well. Nice radius on the front there. And the spring for it, and we'll go through the details on the spring, but I can tell you now, my experience with AFR heads is that their hardware is always top quality. I once remember saying to Rick, I don't understand how you make any profit on your heads. Your valves and springs must cost twice what everybody else's do. And I think his response was along the line of, he says, well, you know, quality does cost. And I said, yes, but your prices aren't any higher than anybody else's, of any consequence, that is. So anyway, that's the basic casting there. Let me tell you what we're going to do with it. Essentially, I'm doing this flow test as only part of a whole test. The final part is going to be when we put it on an engine and put it on the dyno, and put these heads on the dyno, right? And we are going to test with 2 intake manifolds. One, a Elbrock RPM air gap performer, which is a very good head for, a very good manifold for heads like this. And 2, a triple 2-barrel carburetor manifold, which, when you first look at it, the first impression you will get is nothing is going to flow very well through there. But my partner in crime on this project, Jack Sane at Walters Engines, has ported this manifold extensively, so it does flow pretty well. And what it will do, it flows well enough for us to make a useful comparison between the effectiveness of that intake and the RPM performer air gap, which flows pretty good right out of the box. So let's take a look at the valve weight, right? Here's our lightweight 5/16 stem valve, and here's a regular valve, right? So well, it's around 12 grams lighter. So basically our AFR valve at just on 100 grams is 10 to 12% lighter than its regular 343 or 11/32 stem. Right, it's probably not able to see the difference there, but so what are AFR's lightweight valves worth? Anything? Yes. The reduction in valve weight, plus the fact that they come with light steel retainers on these heads, means that the valve train replicates, or say the valve train, the valve mass replicates having titanium retainers instead of steel retainers. A good steel setup is going to save you the cost of a set of titanium retainers for a regular size stem valve. Having lightweight valves is a good approach to making a healthy valve train. It's actually an advantage that the cylinder head manufacturer could exploit by using a slightly lesser quality of spring. But AFR did not choose that route. As usual, as I said, their hardware is very good. And the choice of spring they've made has been a very considered one. So I want to look at that spring in detail now, so that you'll see that this hardware business is not just something I'm glibly talking about. It's actually applied in principle. So first thing, let's take a look at the installed height of the springs and work from there. Okay, let's set the installed height first. Right, let's put that to 0. Right, got that. Now, let's put our spring and retainer in and see what that is. 130 on the seat. Right, now let's see what it is over the nose for a 600 lift at the valve. The spring's capable of 650, but let's leave a little on the little margin here and check it at 600. That's the most likely maximum lift we'll use on a 302 or a 331 or even a 347 for the street. Right, let's go around. Let's do that again. 1, 2, 3, 4, 5, 600. It is 350 pounds over the nose. Right, I already have checked the spring rate, and that is sitting right at 360 pounds. So with its weight and its stiffness, this is a very good spring. Well, we've looked at the spring and at the valve, right? The only other thing I need mention here is that the studs are high quality, the rocker studs are high quality, and the guide plates are those adjustable ones, not the fixed ones, so it allows you to set your push rods up pretty much spot on. No, that's not length, that's pitch this way. Right, next move, let's put this to the test on the flow bench and see where we get to. Well, there we go. That's finalized our tests and we're looking good. Basically then, it looks like the AFR 165 Renagade heads are living up to expectations and maybe a shade over that, so that's good. I've just got all the testing done. Next step, we'll go into some of the details on what it does. Well, the thick line here is our 165cc port AFR Renagade head with the 1.9 inch valve. This, the thin line, that is my E7 TE head with a 202-16 valve combination, right? And had trick valve seat and all this good stuff on there, and a lot of porting, and it was very strong on the dyno, right? You can see that right up until in this range here, that the AFR head shows itself very well, considering it has a much smaller port and a much smaller valve. So that our comparison is a little more fair, instead of comparing them outright, let's look at the flow efficiency, because remember, we're talking about a small valve head versus a big valve head. Well, here we go. The thick line is the AFR intake valve efficiency, and the thin line is my E7 TE head with the 202 valve. You can see up here that we're hitting something like 87% efficient on the AFR head. I can tell you now, this is the highest valve flow efficiency at this lift of any of the aftermarket heads that I have tried, right? That includes at least half of them out there. So one of the reasons why we can expect good performance on this is that this valve at low and medium lift looks a lot bigger. What does a typical aftermarket head have? At this lift it's nearer about 72%, so it's down here, right? My heads typically, my iron heads that is, typically are in the 80% range at this. So, and this is good, better than anything you can buy except for this. So major points for the cylinder head here. Very stout throughout. Now let's look at something that isn't very often talked about, but if you're going to get serious about your cylinder head porting, you have to get into the science of it. This graph here is the port energy density in foot-pounds per square inch per foot. And it virtually dictates the success of a cylinder head in terms of its output. We can look at these numbers here and we can say that anything which goes over about 20 foot-pounds per square inch of valve per foot length of port is going to make big horsepower. Well, look at this. We're up around the 21.5 there, and remember, this cylinder head here produced some really stout figures, and I'll give you an idea. On our 10.5 to 1 motor, it cranked out 1.395 foot-pounds per cube. Check that out with other cylinder heads and you'll see that's a lot better than most of them do, and that's a modified iron head. What we've got here is AFR's not overly expensive 165 Renagade head, and it betters that. So I'm expecting great things from this on the dyno. Exhaust was pretty strong, right? You can see that it's approaching the 200 CFM and hovers around 201, 202 CFM for quite a bit up here. So the thing is we've got a good exhaust port as well. But with a 1.6 valve, there's no reason why it shouldn't be good, and at least compare with other heads. So let's look at it compared with my head with a 1.6 valve. Right, my iron head. Now let's go to there. Now let's go do it the other way around. Here we are, thick line, our Renagade head, thin line, my E7 TE head. Now I have to tell you, these E7 TE heads, you can get a good port if you know what you're doing. Takes quite a bit of skill, but it can be done. So what we have here is an exhaust port which falls into the category of pretty damn good. Maybe could be a little bit better, but really it's well balanced with whatever the intake is. So Airflow's Renagade heads have good flow numbers, good port velocity, a very fat flow curve from efficient valves, and one thing this doesn't show up on here, they're very insensitive to octane rating. In other words, with a well-built engine, they'll run 10.5 11 to 11 to 1 on 87 octane fuel. Now that doesn't come about easy. The heads are capable. You have to be a capable engine builder to extract that. But let's look at this. Here's our flow figures, right? But they don't tell us exactly how much horsepower we're going to get. Now, this is where we could get into something like a simple dyno test to show. But here's the problem with comparative dyno tests, testing stock versus the modified one, is that they may require different camshafts for optimum use. So the IOP program goes through countless, I mean thousands of calculations to calculate what the potential horsepower is, and it's very accurate. Let me show you here. Right, so let's go to here, quit, go to this here, and what I've done here is I've put in, this is our opening screen. I've put in the port area, the flow at the lift we're going to use, which would be about 580 lift. I've put in the bore stroke, the compression ratio, the limiting Mach number of the head. I happen to know what that is, but this program will calculate it for you pretty close. Right, so I hit the calculate button, and here what we've got. It shows that this 331 model engine here has the potential to, on 10.5 to 1, has the ability to crank out 460 foot-pounds of torque, and the port area limitation, so this is when it reaches Mach 0.56, is 560 horsepower. The airflow limitation, now this is a number that's developed, and it assumes that there is no restriction to the intake or exhaust. The engine is perfectly cammed, the friction levels are down at pro stock levels, so this here is a number which you could get if you built something similar in sophistication to a pro stock motor. So that's just a guide there. Usually what happens is we get a number just a bit bigger than that if the engine's done right. You'll notice that there are these boxes down here. Best torque output. This does assume you will install the appropriate cam. For details on the Torque Master cam program, click below. That'll spec a cam out for you. This one here, this is the port area limited power set by the limiting port speed stated as the Mach number that's up there. So this is what we get close to in this instance. This is the horsepower capability of an engine with a specific air consumption of 5.5 pounds per hour. It's corrected for compression, etc., etc. Well, I've gone into details on what that is. Now, let's actually look and see what a real engine did. This engine here was one that I did some years ago. You'll see the AFR, well, you may not be able to, but if you've got a copy of my book when it comes out, you'll see the AFR logos on here. It's a 331 10.5 to 1 motor, right? It had a Super Victor intake manifold, single plane, a Holley HP carburetor. I think that was about a 750. The HEI distributor on this was from Performance Distributors, right? It's a GM distributor adapted to a Ford. Works very well. Now then, tested at Terry Walters Engines. What did we get for power? We got 561 horsepower and 461 foot-pounds of torque. Only 1 horsepower and 1 foot-pound different to the predicted. Now, okay, showing off here. That is a bit closer than we normally see, but this program is very accurate in what it determines the head's capable of. So if you can build your engine right, you will get very close to these predicted numbers. A 10 horsepower error total is about it. So you usually, 9 times out of 10, plus or minus 5 horsepower and plus or minus 5 foot-pounds, right? On a big block it might be a little bit bigger than that. Percentage wise it's about the same. Anyway, our next stage here is to dyno test these heads as I outlined before. That will be in part 2. So thank you for listening, thank you for watching, thank you for putting up with all my stories, and if you like what you see, please subscribe and hit the like button. Thank you very much.